was remarking to me that this is the first time that Connecticut has had this kind of regional conference with New Jersey and New York. And it's very interesting because I guess we're the little kid on the block, and so to speak, when it comes to that group. But so we're very welcome here, and especially when any of the our regional people to recognize that we do have company. Okay, so we look at those regional not more as partners, but part of the family. I think we have to recognize that when we are in.
Well, can you see me? Yes?
You're okay with
Okay, so I may not need that, thank you. I know I'm short, but not that short. Anyway, what I have to say now is somewhat longer perspective than the response to an immediate emergency like the days after a major hurricane. So this gives a longer perspective on climate change and how it may affect the consequences of a hurricane and its impacts. And just to give you an overview of some of the main IPCC results in terms of global warming, the Earth has been warming up for at least over 120 years. And the various climate models that are used to project future conditions anticipate that if we keep putting greenhouse gases into the atmosphere at increasing rates, that the Earth could warm anywhere from 1.8 to 4 degrees Celsius, or about 3 to 7 degrees Fahrenheit by the end of the century. And sea level rise may be anywhere from 7 to 23 inches also within the next 100 years. And that doesn't account for the possibility that the ice sheets may be melting and disintegrating more rapidly than that, and that prospect will be discussed in a few minutes. One of the things that will be of concern is that while we cannot say with certainty that there will be more hurricanes altogether, in general, it's expected that there will be more extreme events of all kinds, more periods of drought, and on the opposite side, periods of intense rainfall and stronger tropical storms, which include hurricanes. So that while the total number of hurricanes may not necessarily increase, and there's a big debate going on as to whether or not that may or may not be the case, but there tends to be, we've already begun to see, or we think we're seeing, a trend towards more intense hurricanes, or typhoons, or cyclones, as they're known in the Pacific. Now, this is a chart showing global sea level rise for the last 130 years. By comparing present sea level trends with those of the last few thousand years, it would appear that the sea level rise began, this current phase of accelerated sea level rise began somewhere between the mid and late 19th century, at a time when the Earth temperature started to warm. It isn't until really the mid-20th century that one can put a finger on it and say that, well, we're beginning to see more and more the influence of human effects, the anthropogenic effects due to greenhouse gas emissions, and also burning down of forests. Anyway, the gray areas on the curve represent the tide gauge data from around the world. The red represent the satellite altimeters that have been up in the air since 1993. And the overall trend for the 20th century has been around on the order of 1.7 to 1.8 millimeters a year. Within the last 15 to 20 years, it's gone up already to 3 millimeters a year. So we may be seeing already an accelerating trend in the recent sea level rise. That was on a global scale. Now we're looking more locally here at New London, and this is what the tide gauge shows for New London. It's almost about 1/10 of an inch a year over the last 80 years or so. And you see a similar pattern of sea level rise throughout the East Coast and Gulf Coast. The rates may vary from place to place due to local factors, which we'll discuss shortly. This is just a regional picture now, the tri-state area from Sandy Hook to New London. Again, from the tide gauges, for the record lengths are not equal. I mean, the start date varies from place to place. New York City and San Francisco have the longest records in the United States and even in the world, because most of the tide gauge records that were kept that we have access to generally begin in the late 19th or early 20th century. Anyway, regional rates at 2 to 4 millimeters a year over the last 80 to 100 years. Now, only part of that local sea level rise is necessarily due to climate change. So this schematic diagram shows the main causes of sea level rise. And the ones that are most directly related to climate change involve things like the melting of ice on mountain glaciers and the ice sheets. So that ice melts and eventually runs down rivers and such and winds up in the ocean. Also, as the air warms, so does at least the upper layers of the ocean. And the warmer the water is, the more it tends to expand, and that would also cause it to rise in level. But locally, that can vary also from the global average. You may have higher than average warming in one part of the world as opposed to another, and so that water will rise higher than elsewhere. Now, other complicating factors of a more local or regional nature are vertical land motions due to geological processes and also human processes. You can have plate motions that generate earthquakes, like we saw in Japan in the spring. So in some parts of the world, the land is rising because of tectonic activity, and in other places it's sinking for that reason. But in another major cause of land motion variations is the response to the removal of the ice sheets from the last ice age. And that ice melted. It started melting anywhere from 18,000 years ago to about 8,000 years ago, or about 10, 12,000 years span. And the heavy load of ice that formerly existed over most of Canada and Fennoscandia, that pressed the land down, and so the land on the edge of the ice sheets, which includes right here and New York City and areas to the south, bulged upward. You know, you press it down in one area, it bulges up elsewhere. And the reverse happened once the ice melted. That land has been rising ever since, and it still is. I mean, if you go to Hudson Bay or the Gulf of Bothnia up, Finland and Sweden, the land is rising there, and sea level looks like it's falling. And in this area, there's still some subsidence as a result of that. You can have local subsidence because of groundwater pumping. I mean, that happens in many cities, like Houston or Bangkok, cities like that have been sinking because people have been withdrawing the groundwater. Now, then you can store water on land. I would tend to say that that tends to be a minor thing. The water you hold back in dams and reservoirs is pretty much balanced by what you're pumping out of the ground for irrigation. And so that kind of tends to be a minor effect on sea level. All right, now in our study, we used 7 of the global climate models from the IPCC with 3 of their emission scenarios, the B1, A1B, and A2, which cover a range of emissions. I think A2 is among the higher of their scenarios. And we selected, now these climate models divide the world into little boxes, little rectangular cells. And and they vary in size from one model to another. That's one problem, that there's not a uniform consistency in the spatial resolution of these models. But anyway, we selected the grid cells that cover the region of Long Island Sound and the area around New York City and the South Shore of Long Island. And the methodology is described in this report, which the full reference is given at the end of the discussion, the talk here. And so basically we started with one approach that was adapted from the IPCC, but we added on several factors to give this a more localized view. We took the thermal expansion of the ocean, which was a global average, and the estimate of the meltwater contribution from the ice sheets and glaciers. And that estimation was based on a historical relationship between air temperature, the rise in air temperature over the last 100 years or so, which parallels more or less that rise in sea level that we saw. I mean, there's a very close association between the rise in temperature and the rise in sea level. And what the response of the ice sheet is, how much ice melts if you raise the temperature 1 degree, how many grams per square meter or whatever for each degree of atmospheric warming. That's what that's based on. So that's a global average estimate. Then locally, we take into account the response to the ice sheets, the glacial isostatic adjustment, as we call it, and the local water elevation, the local changes in water density, the thermal expansion and salinity factors that are due to the local or regional water temperatures. And that was one set of calculations that were done. The other is assuming, well, supposing ice is going to melt a lot faster than that. Supposing, because the climate models as they now stand cannot simulate all of these processes, like one that's shown here. That's the surface of the Greenland Ice Sheet in summer, where the ice melts on the surface and collects in these pools of water that collect in crevasses, and some of these crevasses, or moulins as they call it, extend all the way down to the bottom of the ice sheet. And then there's a thin layer of water at the base of the ice sheet, and that acts as a lubricant and enables the ice sheet to advance much more rapidly. So as a result of that, there may be more calving at the end of the ice sheet, the glacier, where it feeds into the ocean. And there are such glaciers that feed directly into the ocean in Greenland, also closer to home, so to speak, in Alaska. It's not so close to home, but at least in this country, in Alaska, there are a lot of glaciers like that end in the sea. So supposing that happens, so we take the current rates of ice melting, which are much higher than what were reported in the IPCC report, even although that report only came out in 2007. Already within the last few years, we're seeing much higher trends. And also giving an average value of the ice melting at the end of the last ice age, over that 10,000 year period. Now, there were periods within that were even more rapid. But, that's not likely to happen, in 100 years, within the next 100 years. So even this is sort of giving an upper bound to what might happen within 100 years. And we're only looking 100 years ahead. And I'll point out that the story isn't over in 2100. Anyway, this is the projections for 3 decades, the 2020s, the 2050s, and the 2080s. The upper and lower bar represent the full range of, and there are 21 outputs based on the combination of the 7 models and the 3 emission scenarios. So this doesn't give you the total range of all possibilities, but just the ones that were used within our study, but which are probably representative of what is reasonably likely to happen. And so the red horizontal bar represents the median value. So here, basically, the little blue boxes represent uncertainty, and they represent, say, the 25th and 75th percentile, and the 50th percentile would be the red line in each case. And so you see what the range is, that in the worst case, in this set of, in this example, would be up to 25 inches. This does not include the rapid ice melt yet. This is just, the so-called IPCC-based calculation. And here it is shown by decade, the sea level rise for the region by decade. For each individual model, which is each one of those color bars represents the output from each model. So you can see the variations among the models. And for one scenario, the A2 scenario, which was the higher of the 3 that we were using. And so again, in the worst case scenario by the 2090s, you can have possibly up to 30 inches of sea level rise. And what I showed before, by the way, the highest part was for the 2080s, so here's 1 decade further. The other thing to point out is that, it's a slow beginning for the next couple of decades, not too drastic, things that could be handled, but the pace accelerates after mid-century. So that a lot of the planning decisions that are made now need to anticipate the future, even if the worst effects don't necessarily show up until way into the future. So for those projects that involve things like infrastructure or such, building roads or bridges or things of that kind, you really need to think forward, which is a contrast in thinking to emergency, which is reacting to something that's going to happen tomorrow or the day after. Anyway, what if the ice accelerates more so than before, as I mentioned before? And here we're seeing the ice shelves in Antarctica, Wilkins Ice Shelf in Antarctica that broke off. That's on the Antarctic Peninsula, and that was just the latest of a number that had been breaking off within the last 20 years. So what has happened is that the glaciers feeding into the ice, this ice shelf is just floating ice. It doesn't really add to sea level, but it acts as a barrier for the glaciers that on land-based glaciers that are feeding into the ocean and keeps them from reaching the ocean. Now, if they break apart, the glaciers can dump their ice directly into the ocean, add new icebergs, new ice that will, when they melt, they will raise sea level. And this just goes to show, and this is already out of date because I think this dates to the early part of the decade, of the last decade, the 2003, in Antarctica and Greenland. And the red spots represent the glaciers that have been surging, and you can see from the blues, I think, represent areas where the ice has been thinning. The thickness of the ice sheet is decreasing in many areas. And so this just represents rapid ice, what we call the rapid ice melt scenario. So this is just the ice melt contribution when keeping the other factors constant and adding this into the others, and coming up with this curve, which is similar to what you saw before, but it has this added ice melt in it. And now, toward the 2090s, we're getting close to 70 inches of sea level rise, in the high 60s by the, for
Those bars represent
an individual, one of the 7 individual climate models that were used in this study.
so all the climate models are showing a trend.
Oh, they're all showing an upward trend, just they vary in the amount. That's another thing I ought to point out, that in terms of warming, for temperature and for sea level, there's a consistency, if not in the final result, the actual amount, but at least in the trend, in the tendency toward an ever-increasing value. With precipitation, it's a little bit more ambiguous, because some models may predict greater levels of precipitation, and other models may predict just the opposite. So there's a greater uncertainty attached to the results for precipitation than there is for temperature and sea level. And the other thing is, the way we estimated sea level is to a large extent dependent on temperature, because a number of the variables make use of temperature in estimating the sea level rise. Anyway, now let's get to hurricanes, because that's really what we're interested in here. And here we see Hurricane Floyd making its way up the north, up north along the East Coast. And when it arrived in this general area, it did not really create much in the way of coastal flooding. A lot of its punch was already dissipated on its way up, and I guess it was downgraded to a tropical storm. Nevertheless, it still was a major rain event, and it created extensive flooding in New Jersey, in southern New York, and I presume also here in western Connecticut. And so this shows that different hurricanes may have different consequences in terms of the destruction that they cause. In some cases, it may be the surge associated with the hurricane that creates the most damage, like Hurricane Rita or Katrina, for instance. And in other cases, it may just be wind damage and downed power lines and things of that sort. Anyway, this area, even although we're fairly far north, is not at all immune to hurricanes. And, we had quite a few, and this just represents the storm tracks of some of these hurricanes. And I'll just point out a few. The worst that hit this area in the 20th century was that of 1938, also known as the Long Island Express or the New England Storm. And it crossed the middle of Long Island and made landfall not far from here, in fact, and resulted in extensive damage and over 700 fatalities. And there was another major hurricane in 1944, then Hurricane Donna in 1960, and even although its track was mostly across the eastern part of Long Island and southern New England, it caused extensive flooding in lower Manhattan. And I have a picture from the New York Times. It was front page New York Times that day, that people were walking practically hip deep in an area that is near the southwest corner of the World Trade Center site. And Gloria in 1985, which sort of blitzed through the area. It didn't create all that much damage here, but I understand from people that I knew that on the eastern end of Long Island, there were a lot of trees down and power was out for quite a bit after that. And this just shows a dramatic photo from that 1938 hurricane with waves crashing against the seawall. And this is just a historic record of the major hurricanes within the last 200 years, and there have been quite a few of them in this region, so that hurricanes are a part of our landscape and need to be considered in planning. Now, we also looked at the storm surge, this in a semi-quantitative way, because we don't have really the best storm surge model, although we're working with Stevens Institute. They're adapting their surge model for longer-term climate studies. But for the storms of greater frequency, we use tide gauge data, the historic tide gauge data, hourly readings averaged over the period of record. And for the larger storm, like hurricanes, we use the slosh model, and in fact, I'll show you a map. And in general, if you know what the surge levels are, the surge heights, and actually I want to make a distinction here between the surge level and the flood, what I call the flood level, of the water level in a storm, because the surge is that extra rise in water that's caused by the storm itself. The lower air pressure, there's an inverse relation between the air pressure and the sea level rise, and also the winds that are pushing the water forward. And then also the true water level, which includes the effect of tide, because if the tide is, if you're at high tide, then the water level is going to be higher anyhow. So that's just additive. And then, but we don't consider the effects of waves, which are even on top of that. So that's why you can get a lot of damage with some of these coastal storms. Anyway, this is a curve of the return periods of the maximum water levels and storm surges. The water levels are the plot on the left, and the storm surges on the right, present-day conditions for New London. So the FEMA likes to use the 100-year event. So if you extrapolate this curve roughly to the 100-year recurrence, the current water level, the 7.5 feet. So in other words, what that means is that there is a 1 in 100 chance of there being such event in any given year. And for the surge, it's close to 6 feet. If you were to add a foot of sea level rise, let's say, there would be a parallel curve, but 1 foot higher, so that the overall water level and surge level would be 1 foot higher, but the return interval would be much shorter. Instead of one in 100 years, it might be let's say 1 in 60 years, as an example. So that even if the nature of the storm didn't change, even if we're not claiming that storms are going to be more intense or that they're going to be more frequent. Let's say the same kind of storms that we've had in the past. But if you have a rise in sea level, the effects of the surge will be greater. Or putting it another way, the likelihood of a 1 in 100-year rare event will become more commonplace. So there will be more coastal flooding. I mean, that you can expect. And now we're looking at a slosh map. This may be more germane to today's discussion. And this is for a Category 3 storm on a northerly track going at a 60 miles per hour forward speed at high tide. And this simulates the conditions of that 1938 storm, that hurricane that I mentioned before. And the hot spots in terms of the surge are in Jamaica Bay, that's the red area, Jamaica Bay, Long Beach, and Fire Island. Also the western end of Long Island Sound, up the Thames and Connecticut River estuaries, and other scattered locations. And the reason for that is simply a funneling effect. I mean, you've got this storm that's moving on a south to north track. It's pushing the water forward, and it's also rotating counterclockwise at the same time. So the winds are literally pushing the water, you know, from northeast to northwest. And so it piles up at the end of Long Island Sound, and also similarly funneling up toward New York Harbor. So local geography also plays a role. So we said not only the storm itself, but the time of the tide that it hits, and local geography, or bathymetry, maybe more specifically. And we're talking water levels, you know, in the Jamaica Bay on the order of 20, 21 feet for a Cat 3. And in this area, let's see, anywhere from 10, 11, 12 feet of a surge for at high tide, you know, for a Cat 3 hurricane. That's today. Now, if you add future sea level rise to that, you know, add a couple of feet. And so what are the likely consequences? Let's see, how much time do I have, by the way? How am I doing on time?
10 minutes.
Oh, good. There'll be time for questions and answers. So what are the consequences of all this? And the studies that we've done, and I should point out that this is an amalgamation of studies that were done for the New York City Panel on Climate Change, for the state of New York, ClimAid program, as we called it, and in part for the Nature Conservancy. And I was working with our team, you know, the Climate Impacts Group. There were a number of us that also investigated the temperature and precipitation changes for the region. My talk is just focusing on the sea level and its consequences. Anyway, so our emphasis, because of the urban orientation, was on infrastructure and buildings and so on. And so roads and railroads, airports, a lot of these are built very close to sea level, so they could be flooded. And this, of course, is germane to emergency preparedness as well, because it could affect evacuation routes. There could be a tendency toward increased street and basement flooding, and also homes built very close to the shore would be at greater risk. And places like Long Island that still get their drinking water in part from local aquifers, there's the issue of saltwater intrusion into the water supply. And even in the case of New York City, most of whose water supply comes from upstate reservoirs and sources. But, you know, in the event of a drought, we do access water from Hudson. There's a Chelsea pumping station up the Hudson River. And in a drought, the river water level would be lower, but say that sea level was higher, the saltwater front might encroach further upstream and affect that water supply system in the event of a drought and in the event of sea level rise. And then there's always issues about pollution and so on, which I think you are perhaps better equipped to handle. Anyway, to summarize, for those who might be skeptical that the Earth has been warming or that sea level has been rising, in this region there has been a historic rise in sea level ranging from 2 to 4 millimeters a year. The area is prone to hurricanes, and I list some of the more prominent ones of the past century. And we are projecting, fairly significant rises in sea level within the next 80 to 100 years. which are summarized here. These numbers may vary because we're looking, in one case, at the decade of the 80s, and in the other case, at the decade of the 90s. But anyway, by the 2080s, anywhere from 1 to 2 inches, 1 to 2 feet rather, in this area. And if you include rapid ice melt, it could be considerably more than that. And using New York City as an example of the recurrence, the shortening of that recurrence interval, the 100-year event may become the 15 to 35-year event. And at West Hampton Beach, somewhat longer interval, 35 to 60 years. But yet a considerable shortening of that flood return period. And, you know, for those that are concerned even with the smaller storms, the nor'easters, that places that tend to get flooded regularly every time there's a major nor'easter, I mean, they're really going to feel it. And so we mentioned increased flooding and inundation, saltwater intrusion. I didn't say anything about beach erosion, which is a major concern in places like northern New Jersey and the South Shore of Long Island, maybe to a lesser extent here because you have the smaller pocket beaches. You don't really have these long, extensive barrier beaches. But still, you know, the Army Corps regularly replenishes a lot of these beaches, renourishes them, and these cycles of renourishment, you know, what may have been done once every 10 or 20 years, these periods may become shorter and shorter. And then there's also the, so there's that additional expense, and also the rebuilding after major storms. You know, how many times will FEMA bail you out after each hurricane and your home is damaged or destroyed? So, you know, these are all things that need to be considered. So these are recommendations that, as I say, are to be looked at on the longer term, but also apply to shorter term emergencies. That the state and local adaptation plans need to take sea level rise and storm data into consideration, both in long-term planning and also for their emergency response awareness. And then over the longer term also, I think that coastal land use planning is very important. And it would be very desirable to acquire as much remaining open space and natural habitat as possible, not just for ecological reasons, but to act as a buffer against the storm surges, and also to allow for inward migration of salt marshes and the like as sea level rises. And in doing that, one should identify those areas and populations, assets and populations that are potentially at risk to flood and storm damage today, as well as taking into account possible future scenarios. And these vulnerabilities should be communicated not only to the decision makers, but also to the public at large. I mean, people should be aware of the risks associated with living close to the shore. And there should be a coordination among the various local and regional entities to pull together information on the coastal hazards and have these updated on a regular basis and adjust their plans and regulations accordingly. And this is the published reference that's available on the web, which describes the methodology that was used in that case specifically for New York City, but which can be adapted to other parts of the country as well. Other cities, other parts of the country can benefit from our experience in New York. Okay, are there any questions? Yes?
So the common wisdom is that warmer waters tend to feed hurricanes. And I wonder, one, if that's true, and if it's true, do the scenarios that you present of potentially warmer waters mean that we are likely to see either more intense hurricanes, hurricanes that stay in the area for a longer period of time? How is that related to the water temperature?
Well, at first glance, yes, increasing water temperatures would seem to increase the number of hurricanes, but then there are countervailing effects as well, and one of those is wind shear. And so if you have upper winds that tend to sort of move at cross purposes to here's a hurricane that's building up, and it tends to build up vertically, you know, there's this vertical convection, and here comes this wind at a higher elevation that tends to lop off the top of it. It may prevent it from getting full force. So there are these opposing factors, so it's not, you know, a clear-cut one-to-one relationship. Although it may seem so, you know, it's easy to, you know, to say that. I thought that too until it was explained to me.
I have a question. In terms of the linkages between hurricanes and climate change, would you say we're talking more about frequency or intensity? And is there any new research since 2005 to suggest that that linkage is stronger than it was, say, since Hurricane Katrina? Thank you.
The first part, I think that to say that hurricanes will be more intense, I think that's on firmer ground than they will increase in frequency, because that is being debated. And yes, there have been recent publications. I don't have that at the tip of my fingers right now, but I can dig them up if you're interested.
On the topic of saltwater intrusion, is there an equivalent to the slosh model maps for groundwater?
I don't know that offhand. I think that's a good idea. There ought to be. Any other questions?